For embedded systems today, I wanted to start out with doing bitwise manipulations. And let's just say we have a char, and I'm going to be boring and call it val. And let's just make it equal to 0x f a. If you're not familiar with this, this is going to be in binary. I'll write it out really quick. 1, 1, 1, 1, 1, 0, 1, 0. Break it apart. That into the two sections. This is f, and this is a. And so what we can do with this now is I need to be able to individually set and clear bits without messing with. So imagine that I don't know what val is in the first place. I want to be able to individually set and clear bits. And the question is, how are we going to be able to do that? And the answer is that there's already one. So if I say, we'll do the longhand version, val is equal to val, ORed, so that's not an L, val ORed with 0x01. So once again, we're going to go through this 0, 0, 0, 0, 0, 0, 0, 1. And we're going to OR them. 0 or 1 is 1. 1 or 0 is 1. 0 or 0 is 0. And you can see that from this point on, anytime that there's a 0, it's just going to translate through what was in the original 1. Okay? And so this turns into something a little bit different. It looks like it's FB. Okay? And so that's what that turns into. And so if we take a value and equal it to itself, ORed with something else, then we get what's called a bit set. And there's shorthand for this. Val OR equals 0x01. What's really cool about this is if we were to change this just ever so slightly, okay, and make this f. This is why this is useful, is when we do this, well, it's going to set all 4 of these bits, whether they're set or not. Okay, and these 4 remain unchanged. So there's 4 bits, and this just turns into FF. Okay? And so it doesn't care whether it's set or not already. And it didn't mess with the rest of the bits. Let's do maybe a different example. Okay, we're going to OR this with 3, 0. This shouldn't change anything, but it doesn't matter. 0, 0, 1, 1, 0, 0, 0, 0. And the whole point is these 2 zeros are going to come through unscathed, right? Because the first 4 bits, sorry, the least significant 4 bits, 1, 0, 1, 0, are just going to be translated through 0 or 0 is a 0, 1 or 0 is a 1, etc., etc. 1 or 1. And these 4 are not going to change at all. But we didn't know what it was before. And so especially if we don't know what something is before, this works really well. So OR equals is bit set. Okay? And something that's kind of cool with this as well is, as you are all new to probably hexadecimal for a lot of you, we can say something like val OR equals, and then in parentheses I can say 0x01, 0x04, 0x20. And you could go back and look at this and say this is bit 0, this is bit 3, nope, sorry, that's bit 2, this is bit 5, yeah. And so we just OR them together within this, and it'll do the math for us. That's kind of handy. Okay, we don't want to be putting too much brain power in it, or we can put this all in together if you really want to. And you can go 0, 0, bit 5 is there. Nope, that's 6, 5. And then we have 0, 1, 0, 1. Okay, and you can turn this all into 1, 0x, 2, 5 is what that turns into. Okay, and this is still a new concept that we're treating bits in a hex value. It seems kind of horrible, but this is what it ends up being. But this was a lot harder to come up with than just ORing individual bits. And so let's just go through the bits really quickly so that you understand. 0x01, this is bit 0. 0x02 is bit 1. 0x04 is bit 2. 0x08 is bit 3. That's our first 4 bits. And if we want to show this in binary over here, I'm just going to show the lower 4 bits. Okay, and then this translates directly up to the upper nibble. 0x10, 0x20, 0x40, 0x80. This is 4, 5, 6, 7, in total 8 bits. And then these just translate up to the upper nibble. I'm not going to write them out, but you get the idea that these go through this way. And so that's what we have to deal with. That's kind of it's confusing because you're like, bit 1 is a 2. Oh, jeez, that's annoying. But when we think about the binary, it starts making a lot of sense. Bit 3, oh, that's 0x08. And once again, this is a powers of 2 thing, right? This should make sense that this powers 2. The biggest problem with this is because we're an octal, we go from 8 to 10 instead of 8 to 16. This is 16 in decimal. So that should help us with that. But the other thing we need to do is, what if we want something to turn into a 0? Okay? And we have our val, it's equal to 5a in hex. Okay? And just so that you know what that is, 0, 1, 0, 1, 1, 1, sorry, 1, 0, 1, 0. This is our upper, this is 5. That's A. And so what we want to be able to do with this as well is we want to be able to set individual bits to 0. And so I'm just going to try to set the upper 4 bits to 0 to clear them, bit clear. The way that we do this in longhand is val is equal to val, and then we have to AND it with something. And if I want to clear the upper 4 bits, I'm going to AND it with this, because this is how it looks. Let me line this up here. 0, 0, 0, 0, 1, 1, 1, 1. So we AND them. 0 and 1. That's still a 0. 1 and 1. That's a 1. 0 and 1. That's a 0. 1 and 1. That's a 1. 1 and 0. Oh, 0, 0, and oh. Because all of these are 0, I just cleared these 2 bits, but essentially I cleared all 4. It doesn't matter what they were. And so this is going to give us 0A. And I did it. I cleared the upper 4 bits without messing with any of the other 4 bits. We can do this to individual bits. And so what this looks like, and with 0x, in this case 0x0f, is what this looks like. But this is a negative of what we want. And what we actually want here is, what we can do is, I'll just trade this out a little bit. I'm going to do a tilde, which you should have gotten from a previous lecture. And I'm telling it which bits I want to clear. It's kind of a double, triple, quadruple negative someplace in there. But we're knotting this, which turns it into 0f, and then we're ANDing it with here. So bit clear, the shorthand is AND equals tilde, and then I put all my arguments in this. Let's have some fun with this. Val is equal to 0x 3, 7. Okay, kind of an odd number, but 0, 0, 1, 1, 0, 1, 1, 1. Okay, if I do val and equals tilde now, knowing that it's 3, 7, with 0x, and I'm gonna say bit 1. Okay, 0x02. Remember that bit 1 is a value of 2 from previous. Yes, it's hurting our brain, I can tell already. 0x02, going to give myself some help here, some space, 0, 0, 0. Okay, and we're going to tilde this, 0, 0, 0, 0, 0, 0, 1, 0. We're going to tilde that, which gives us 1, 1, 1, 1, 1, 0, 1. When we AND them, 1, 0, I cleared that one bit, and the rest of these are just going to translate through. Okay? And this turns out to be 0x3, 5 is what ends up happening with this. Okay? And that's what happens. And equals tilde, and we can just put in the parentheses all the bits that we want to clear. So val and equals tilde, and then in parentheses we can put in 0x01 and 0x, and this is ORs between the 0x 04, okay, that's going to be bit 2, this is going to be bit 0, okay, and so now I can clear these. So this was our thing, we're going to clear bit 2 and bit 0, which is this is bit 2, this is bit 0, and we're just going to end up with 0x30. Because what this does, this tildes it, and we get 1, 1, 1, 1, 0, 1, 0, 1. I did that wrong. 1, 0, 1, 0. I'm trying to cut corners and go faster. 1 and 0. It's an AND. Remember, this is an AND. Previously, for the bit set, it was an OR. 1 and 0. 0. 0 and 1. 0. 1 and 0. 0. 0 and 1. 0. And then this translates directly through because these are all 1s. 0, 0, 1, 1. And that's just 0x3, 0. So this gives us an idea into bit set and bit clear, and this should be really helpful for you for the future.